Okay, good news. This is the last of the concept lectures based on basic chemistry. So we've gone through quite a lot so far, and hopefully many of you have had chemistry already in your student lives, so this shouldn't all be completely new. But if it is new to you, this stuff is very important that you do understand what I've talked about in these lectures, because this is going to form the basis of your physiological knowledge. So if this stuff isn't making sense, you need to seek help. You can talk to me, we can potentially set up video chats like this. Seek a tutor. We can do tutoring over summer, we can do it in an online environment. That's possible, so talk to our tutoring department, which is, I think it should be in the syllabus. If not, contact me and I'll get you the details for that. But make sure this stuff is making sense. Now, the last part of this is no less important than the other parts I've talked about, because acids and bases are extremely important in terms of the balance inside, or the homeostasis inside the human body. One very, very good example of that is that our blood needs to stay at a pH of between 7.35 and 7.45, so very small changes are allowed in our blood. Once we move out of that range, if we're getting lower than 7.35, we're entering something called acidosis, or acidic blood. This can have very, very dangerous effects on all the things that are going, which are basically dissolved in the blood, or being carried by it to the cells. So consider our blood and our blood vessels as the main interstates in America. And then think of all of the cities, the towns and the villages being fed by these interstates, by these large trucks just driving all across the country, delivering goods and services to the various populations. Well, that's basically what's happening in the blood to the cells. The cells are the cities. You can kind of think of like organs as cities, and then, we'll say organ systems are cities, organs are towns, the cells of those organs or tissues are villages. All of these need fed with the blood, because the blood carries the trucks with all goods in it and then takes away all the wastes. If our pH starts changing in the blood, it's kind of like turning the roads from just normal sunny weather into icy conditions with, lots of oil dumped on top of it. It becomes very dangerous, and a lot of those trucks won't make it to their destination. So then think about all of those villages, towns and cities that are going to start to suffer as they run out of their supplies and their waste starts to build up. So pH is incredibly important in the blood to maintain 7.35 to 7.45, to make sure that all of those things that are going to the cells and all that waste coming out of the cells are basically being done. So what is pH? pH means power, P, of the hydrogen, H, ion. So power of the hydrogen ion. Why do we use the hydrogen ion? Because we are 67% water. And water is H2O. If water is broken or split, which it often is, you can end up with one hydrogen and one OH. OH is known as hydroxyl. It's an ion because the hydrogen, remember this is a P with an electron, the electron goes to the oxygen, it's broken off, so that's one P, so that's a positive proton. So that's why the hydrogen now is an ion. And what's left is this OH, or hydroxyl, hydrogen plus oxygen, hydroxyl, and it's negative because it's picked up that electron. So water, H2O, essentially equals that plus that. Hydrogen ions and hydroxyl ions. That's positive and that's negative. If you've got 1 and 1, you've got no charge, it's balanced. Now on the pH scale, that means you are here. So a glass of water has a pH of 7 because the hydrogen ions equal the hydroxyl ions. And remember, if you join those two together, you end up with H2O, or water. So you can separate them and rejoin them. Now, the reality of that is a little more complicated in terms of, you know, the bonding, but in terms of us understanding it and thinking about it, this is fine. We'll stick with this. So pH, or the level of acidity in something, is based on how many hydrogen ions are in there compared to how many hydroxyl ions. So when they're equal, that is what water is. And it's a pH of 7, so it's in the middle of the scale. The scale goes all the way down to 0 and all the way up to 14. So let's think about some of the terms. An acid and an acidic solution are different things. An acidic solution is any solution which is less than pH. So a solution of pH of 0, 1, 2, 3, 4, 5, 6, 6.9, 6.99 is an acidic solution. A basic solution is anything greater than 7, so 7.00000001, it's technically a basic solution, all the way up to pH of 7, so pH of 14. Now, so what is an acid? An acid is any molecule that can donate hydrogen ions to when it's put into a solution. So you got your solution of water at pH of 7, you put in your acid and it donates more hydrogen ions than hydroxyl, and so it drops the pH below 7. Or if it was a pH of 5, it would drop it below 5, it's added more acid. Or if it's pH of 11, it would drop it toward 10. So it's going to move it down toward the acidic side. Or if it's in the acidic side, keep it going down. A basic solution, a base or an alkali does the opposite. It absorbs hydrogen ions and therefore increases the ratio of hydroxyl ions against hydrogen ions. So it moves it up the scale. So remember, acidic solution below 7, basic solution above 7. An acid gives hydrogen ions to the solution, moving it down the scale, wherever it's starting from, and a base takes the hydrogen ions, increases the proportion of hydroxyl ions and pushes it up the scale, away from acidic toward the basic. Finally, a buffer. A buffer is a molecule which can do both things of an acid and a base. It can give hydrogen ions as the solution moves up, moves more basic, and it can absorb hydrogen ions when it moves down, becomes more acidic. So what a buffer does is it maintains a specific pH. So if you have a buffer at pH of 4 and you put another mystery solution in which happens to be more acidic and you're adding hydrogen ions, the buffer will absorb the hydrogen ions and maintain pH 4. And then if you add a second solution which absorbs hydrogen ions and is going to push it upward, the buffer will then start releasing hydrogen ions to the solution and to maintain it at the pH of 4. Now for our blood, remember at 7.35 to 7.45, we have two different buffers. We have a bicarbonate buffer and we have a phosphate buffer. And they both try and maintain the pH of 7.35 to 7.45 at all times. But like any system, buffers can be overrun just in the same way as your bath can overrun if you don't have if you block the drain valve, etc., or release valve, and it just starts building up. So those are our terms. We know where our power of hydrogen ion comes from. It's water split into its hydrogen ion and hydroxyl ion. I just rubbed that with my, there we go, t-shirt. So the scale itself, well, the scale goes from 0 to 14. We know that pH now is hydrogen ions equal hydroxyl ions, and pH of 6 means you've got more hydrogen ions than hydroxyl ions. pH of 5 means you've got even more hydrogen ions compared to hydroxyl, but how much? Well, this scale is called a logarithmic scale. And a log scale means that when, instead of you going from 7 to 6, which is a difference of 1, it's actually, on a log scale, a difference of times 10. So if you've got the same number of hydrogen ions and hydroxyl ions at a pH of 7, you're going to have 10 times the hydrogen ions compared to hydroxyl ions at pH of 6. At pH of 5 you times it by 10 again, and you end up with 100 hydrogen ions for every hydroxyl ion. So at pH of 4, that takes it up to 1,000. You take that away now because it's not equaling it anymore. It's now a ratio. And that goes down. So that's 1,000, that's 10,000, that's 100,000, that's 1,000,000, 10 million. So when you're getting down to the pH of 1 and 2, sulfuric acid, things like that, you've got 1,000,000 more hydrogen ions than you have hydroxyl. So you've got all these positive charges just focused. Now remember from your chemistry, you want to have a full outer shell. So a hydrogen ion is going to try and break up molecules so it can bond and get its electrons and become stable. So it will just break things open, which is why you can see acids burning a hole way through something, because it's opening it all up and making bonds with it as it goes. So at pH of 6 that's almost imperceptible because it's just like 10 times as much, there's not a lot, but at pH of 1 where you've got 1,000,000 more, then a lot more of this is actually going on. Now the exact opposite is occurring from pH of 7 and going up to 14, and never forget that the strength of the hydroxyl ion, as it increases exactly in the same way against the hydrogen ion here, so you're timesing 10 going to pH, so you've got 10 for every one hydrogen ion, and that becomes 100, that becomes 1,000, that becomes 10,000, 100,000, 1,000,000, etc. up to 10 million of hydroxyl ions more than hydrogen ions. And the same thing happens, the hydroxyl ions will break open molecules in order to try and stabilize themselves. So severely basic solutions are just as dangerous as severely acidic solutions, which is why your oven cleaner, which is probably the most toxic thing I can think of on the market, even more toxic than bleach, is a pH of round about 12 to 13, because it literally just eats away at all the stuff which has been baked onto the inside of your oven, and literally just chews it up, breaks it open and breaks it off. You leave it on for an hour and then you scrub it all off. Make sure you wear very, very thick gloves. Usually 2 or 3 pairs would be safe. So if you get any on your skin, it's just going to start burning through your skin. So it's a logarithmic scale going up and down. As it goes from 7 to 0, it's becoming more acidic, and 7 to 14, it's becoming more basic. When it becomes more basic, you've got more hydroxyl ions than hydrogens. When you're going to more acidic, you've got more hydrogen ions than you have hydroxide. And keep that in mind, because we're going to talk about acid-base balance again when we're looking at buffering in the blood. We're going to look at it in the lungs when we are blowing off carbon dioxide or etc. And again we're going to look at it in the kidneys, because again we maintain our buffers etc. and our pH very much by the kidneys of reabsorbing and releasing ions which are either we're short of or they're in excess. So that's it for chemistry. Thank you for listening to this particular topic, and we'll move on next and start considering cell membrane transport.